Cardiac output is a topic that's covered pretty extensively in the lab environment. We'll look at the amount of blood that leaves the heart in a given minute and how that's influenced by heart rate and stroke volume. So we need to understand what controls cardiac output. What are the variables involved? How can the body increase and decrease cardiac output? We're going to look at a concept called total peripheral resistance and how that impacts blood leaving the heart. And then finally, when all is said and done, we'll look at some hormonal mechanisms that relate right back to our last topic of blood pressure changes to see how that affects with cardiac output, stroke volume, and heart rate. Cardiac output, if we want to break it down into the simplest definition that we have, is the product of stroke volume times cardiac rate. Cardiac rate being heart rate, number of beats per minute. Stroke volume is a new term for us. It's the amount of blood that leaves the heart with a single beat. So cardiac output is the amount of blood that leaves the heart in a minute or in a period of time. Stroke volume is the volume of blood that leaves per beat. And heart rate is the number of beats per minute or in a given period of time. When we look at a diagram as such, we're going to be coming back to this diagram because, again, I've been trying to reinforce where to start to look to work your way through some of these problems, and we're going to be coming back to this. But we can see that cardiac output is a product of heart rate and stroke volume. And then we've got a number of other variables that affect the heart rate and the stroke volume. First of all, parasympathetics. On this diagram, whenever you see the dotted line, it means it's inhibition, it decreases it. Parasympathetic nerves decrease heart rate. Sympathetic nerves increase heart rate. Now, we're not going to beat a dead horse and go back over that topic. Now, we've already covered heart rate changes. So, at this point, if you're not familiar with that, I'd suggest you go back and you watch that particular lecture for the details on how those two halves of our autonomic nervous system influences heart rate. For stroke volume, however, we've got a number of variables that we haven't even really gotten into much yet. We've got our sympathetic nerves. Not only do they increase heart rate, but they increase the contractile strength of the cardiac muscle cells. They increase the cellular permeability, the calcium, increasing their contractile strength. Stronger contraction, more blood pumped in a given beat. We've got a concept called the Frank-Starling phenomenon as a result of our end-diastolic volume. That's going to give us an increase in contraction strength. And again, increase in contraction strength gives us a greater volume moved per beat. And then finally, we've got the mean arterial pressure, the pressure that's already outside the heart, that the heart has to overcome if it wants to move blood in that direction. Blood will only move from a high pressure to a low pressure. So if the arteries have already got a certain amount of pressure in them, we have to overcome that pressure to get blood to move in the direction that we want. So stroke volume is where we're going to pick it up. Again, if you want to talk about heart rate, go back and look at that particular section. But stroke volume is where we're going to pick it up. The first variable is that end-diastolic volume, or the Frank-Starling phenomenon. It basically says that the higher the end-diastolic volume in the ventricles, the stronger the contraction that the ventricular muscle is going to have. This is going to be viewed as an intrinsic control. It's a reflex as such based on the amount of volume we have in those ventricles just before they constrict. The sympathico-adrenal stimulus on the cardiac muscle increases stroke volume, gives us a stronger contraction strength. This is going to be viewed as an extrinsic control. And then finally, I leave left a little space here, resistance works against those two. Both of these phenomena act to increase that cardiac function, increase the stroke volume. The resistance, however, is something that has to be overcome with increased contraction strength of the ventricles. To go back and look at a couple of terms that we've mentioned a number of times already, systole and diastole. Systole is the term given to the ventricles when they're in their constricting phase, generating pressure and ejecting blood. The diastolic phase is when the ventricles are relaxed, the low pressure half of the cardiac cycle, and the ventricles are filling. It's important to realize that these are not instances in time. Going from systolic to diastolic is not turning a light switch on and off with no gray area in between. These are a continuum of time. Remember, we're discussing the heart contractile cycle as a period of time. From the time the SA node depolarizes and we see a wave of contraction go over the heart to each half of the heart, developing pressure, moving blood through that organ unidirectionally. It's a period of time. So if we say a heartbeat lasts a half a second, you're going to spend part of that half a second in your diastolic phase for the ventricles and part of that half a second in the systolic phase for those ventricles. So rather than viewing them as instances, you can take each half and break it down further. You can have an early systolic phase. The ventricles are just about to contract. They're just starting to shorten. No blood has even left the heart yet. They've just started to contraction. You move into a mid-systolic phase. Now the ventricles are well into their contraction and they're starting to eject blood. And at the late or end of the systolic period, the last little bit of contraction, the last little bit of blood ejected from the ventricles. Now the ventricles start to relax. Now you've tipped over into your diastolic phase. They've started to relax. No blood's even really started to enter them yet. The mid-diastolic phase, now they're half filled or mostly filled with blood. Now you got that late or end diastolic phase. The period of time just before the ventricles contract, and move right back into a systolic phase again. The amount of blood in the ventricles at that time helps dictate the contractile strength. And the relationship that we see by Frank Starling's phenomena is the higher the end diastolic volume, the stronger the cardiac muscle will contract. The higher the end diastolic volume, the stronger the cardiac muscle will contract. You've already studied neuro. You've already looked at stretch reflexes in the skeletal muscle. Just to refresh you, you sit on a doctor's table, your legs dangling, takes a little hammer, he hits you there, and the leg pops out. A quick stretch of a muscle results in muscle contraction. Look at it in a gym scenario. You hear people with trying to do a 1-rep bench press, and they say to people who let the weights drop down quickly and then push back up, oh, they're cheating or letting the weight bounce off the chest in order to be able to lift it. Dumbbells don't bounce off of human tissue. What's happening there is as they let that barbell come down to their chest quickly, it stretches the pecs, it stretches the triceps. The quicker they drop it down, the more they can use that stretch reflex to generate more force, as opposed to bringing it down, pausing, and then trying to push. They're using the stretch reflex that's naturally occurring to generate more muscular force. If we stretch the cardiac muscle, it's going to respond with a greater degree of contraction. And that's what winds up happening. The more volume we see in the ventricles just before they're about to contract, the more stretch is going to be put on the wall of the heart. That stretch gives a stretch reflex-esque phenomena, and we get a resulting stronger heart contraction. That stronger heart contraction means more blood leaves the heart. So when we see this muscle stretched, you see an increase in the interactions between the actin and the myosin. You see an increase in the stimulatory effect of the calcium. This is also what we wind up seeing with the sympathetic nerves to generate a stronger contraction. Anyway, end result is the greater the end diastolic volume of blood in the heart, the greater the heart contraction strength is going to be, therefore the greater the stroke volume is going to be. Extrinsically, we're well familiar with the sympathetic nervous system, increasing heart rate, right? Well, also increases stroke volume. As I said earlier, it increases that calcium availability. We need calcium for muscle contraction. And again, if that doesn't sound familiar, go back and look in your textbook about the regulatory proteins in muscle. Troponin and tropomyosin. They hang out in the way, keeping the actin and the myosin from interacting. We introduce calcium, those regulatory proteins get pulled away. We wind up seeing, through our sympathetic innervation, an increase in the stimulatory effect of calcium as part of that contractile cycle. Total peripheral resistance is the resistance of blood to be injected from the ventricles. You have the concept of preload and afterload. To get an increase in contractile strength, you're preloading the muscle of the heart with that increased volume. And as a result, you're getting that increased stroke volume. Well, as soon as the ventricles relax, there's an afterload in the system. You've got these valves in the heart that will always give way to the strongest force. The ventricles constrict, generate a higher force that's in the aorta, and we will push open the semilunar valves and blood will flow through it, going from a high pressure to a low. When the ventricles relax now, suddenly the pressure in the aorta is greater than the pressure in the ventricles, and the semilunar valves slam shut. If we've got a hypertensive situation, the pressure on the outside of the heart is going to be stronger. Now, with a normal heart contraction, now maybe the semilunar valves don't open as much as they normally would. Maybe they don't stay open for as long as they normally would. Less blood is allowed to leave before those valves are slammed shut again. And that's why we wind up seeing situations like hypertrophy in the heart. If your heart's having to work hard over a long period of time, the muscle's going to get stronger just like any other muscle would if it was worked. But of course, with muscle, we've got the paradox that the thicker the muscular wall gets, the stronger it gets. But now the volume of the chamber is going to be smaller as a result of it. So you always got that counterintuitive nature when it comes to the heart. Stroke volume, as a result, is always going to be inversely proportional to total peripheral resistance. The higher the resistance, the lower the stroke volume. We looked at this dropping off of pressure as we go through the system. And for someone who would have an overly high total peripheral resistance, it's like we've taken that entire slope and simply raised it. Increase the pressure in the system. This could be secondary to hardening of the arteries. It could be secondary to a fluid retention. But whatever the case may be, higher pressure in the system means greater strength has to be developed at the heart in order to still move the same amount of blood. So let's go back for a moment and look at this. The first thing I want to look at here, this is going to pertain directly to lab, is the relationship between heart rate and stroke volume. Yes, we've got the relationship that if we multiply them, it's going to give us our cardiac output. But these are not purely independent events. Because we've got the heart and the number of beats it has per minute, and we still have the heart and the amount of blood moved per beat. Remember when we did heart rate? Particularly, I'm hearkening back to that one slide where we had our control heart rate, normal resting heart rate at the top, and then we had our sympathetic changes to get an increase in heart rate, and then we had our parasympathetic changes to get the lowering of heart rate. If you recall, We talked then about the electrical activity at the SA node. And as soon as we get a depolarization, we get a heartbeat. If we wanted to change heart rate, we didn't change the action potentials. We changed the pacemaker potential. So all we did to get a higher heart rate was decrease the time in between the beats. But I've also stressed that when we're talking about this topic, we're talking about the same period of time from different contexts. So yes, increase heart rate, we remove some time between the beats. But from a blood flow perspective, what's happening during that pacemaker potential? In between the beats is when the ventricles are filling. If we want to get a higher heart rate, we've got to cut down the time in between the beats. Therefore, we get to cut down the time that the ventricles have in order to fill with blood. So now, as you look at your lab and you go through your experiment, you will notice that as heart rate goes up, stroke volume goes down. You may get more beats per minute, but the volume of blood moved per beat drops. Now, early on, with mildly elevated heart rate, that's still going to give you an increase in cardiac output, because heart rate is king. Increasing the number of beats will offset the amount of volume we lose per beat. But there's going to become a tipping point. If stroke volume decreases as heart rate increases, at what point do you go to zero with your stroke volume? Now, what is that? Second grade math, first grade math? Anything times zero is zero. If every time we beat, no blood is moved, then it hardly matters what the heart rate is. Cardiac output is also going to be zero. That magic number is around 160 beats per minute. As heart rate continues to elevate, stroke volume drops down. At about 160 beats per minute, the limitations on stroke volume become so catastrophic that now cardiac output also starts to crash. So we want to take into consideration the limitations on this. We can't raise one without getting consequential changes on the other. So as you're working your way through these paradigms, also keep in mind what drives this. This is driven by the state of the tissues again. And I know I keep bringing this up every single time we talk about it, but anybody can memorize this chart. However, just memorizing this chart won't necessarily help you answer the questions that you're going to be posed with. If you start doing jumping jacks, I don't know why I always say jumping jacks. Jumping jacks. I don't have some sort of weird interest in jumping jacks. But if you start doing jumping jacks, the changes that we see at the tissue level that we've been talking about for the last couple of classes, carbon dioxide raises, oxygen goes down, pH goes down. You are going to see the tissues asking for more blood. Chemoreceptors send signals into the control centers in the brainstem. The brainstem now sends signals down your sympathetic fibers to increase the heart rate, get more blood moving through the system faster, to get those tissues the oxygen they need, to whisk away the carbon dioxide that's being produced. And by doing so, we wind up moving more blood per minute. So always, again, think about this from the tissue standpoint first. Receptor, control center, effector. We won't get an increase in cardiac output simply because the sympathetic nerve said so. These are tools that the control center uses if the receptors give them information that the body has become outside normal parameters. So always keep that in mind. And when you look at your lab this week, it's going to reinforce this cardiac output scenario.